Hello everyone and welcome back for another video. This time we're going to talk about polar equations and graphs. Previously we talked about polar coordinates where we introduced the polar coordinate systems. And in this lecture we're going to continue on, and we're interested in graphing polar equations. Now, polar equation, an equation in the form r equal f of theta. So in other words, r is given as a function of theta. Now, sometimes r and theta are implicit. That means you don't have explicit form r equal f of theta. They could be mixed together. So either implicit or explicit form, we have an equation in r and theta, and therefore a polar equation. Now we want to know how we're going to graph these on our polar coordinate system. So here I have downloaded my polar grids, and we're going to do quite a few examples here. So let's get right started. Now sometimes we could identify the polar graphs by converting them to rectangular form. Okay, so for instance, let's say my polar equation is r equal -4. -4. Notice I have a negative number for r because r can be any real number. So to graph this thing, I can either rewrite this as r plus 0 theta equals -4. So this way I have both r and theta in my equation. And once we generalize this, there's really no need to have that 0 theta in there. But for now, because theta is missing, I like to write it in with a coefficient of 0. So I haven't changed the equation. Now the fact that I have 0 theta suggests that theta can be any real number, right? So for example, you can choose theta to be 0, theta to be in degrees, could be 10 degrees, 20, 30, 40, whatever the measure of the angle. It's pretty much the equation is independent of theta. So the value of r is always -4. Okay, now let's say if I want to get a point out of this one so I can plot it on my grid, I'm going to let theta, for instance, be 0, and then I'm going to let theta be pi over 6 and pi over 2. Just these three numbers will suffice. So when theta is 0, r is -4. Theta pi over 6. Well, 0 times pi over 6 is 0. Again, r is -4. So, and this is what I was saying. The value of r is independent of theta. Theta could be anything. Now, if I plot the point as an ordered pair, r comma theta, right, in my polar grid, so this is going to be -4 and whatever the measure of the angle is. All right. Notice the radius does not change. It's always the same. The radial distance, that is. So -4 is 0. Well, theta 0 is here, right? I'm plotting it on my grid now over here. So when theta 0, r is -4. Well, I go 0 and 4, right in here. This is 0, 4. Remember to plot negative r, oops, sorry, r first, angle second, r comma theta, right? That's how the ordered pairs are. So I'm actually plotting 4, 0. Now I want -4, 0, so we'll reflect it across. So this is going to be the point, -4, comma 0. Then I have -4 and pi over 6. So over here, I do 4 and pi over 6, then reflect it, you get a point right across over here. There you go. That will be my second point, -4 pi over 6. And the next one is pi over 4, so 4 and pi over 4 will be here, -4 pi over 4 will reflect it here, and you can kind of see where this thing is going. The radius doesn't change, the measure of angle is allowed to change. So if I connect these dots, you can kind of see the graph ultimately is going to give me that, a circle, right? Therefore, the graph of r equal -4 is going to be a circle. Now the radius of this circle is going to be, radius is absolute value of -4 because radius is positive, so radius is 4. You see that? Now we can generalize this, and here's another way, by the way, I could have done this. Remember the relationship between Cartesian and polar form. I can actually, if r is -4, I can square both sides of this equation. So r squared is 4, and change r squared to x squared plus y squared. And you can see in this, in the Cartesian form, that this is the equation of a circle whose center is at 0, 0, and the radius is, r squared is 16, not 4. I went and took the square root of 16. So there we go. -4 squared is 16. So there, r would be 4. Positive square root of that. R is 4, which is exactly what we got up here. And here we recognize again the equation of a circle of center at 0, 0, radius 4. And we can graph it on the grid. So we can generalize this, right? In general, the equation r equals a. This is going to be the equation of a circle. If we can identify the equation, then we just, without plotting points, we can just graph them. So this is going to be a circle whose center is at 0, 0, and the radius is going to be equal to absolute value of a. Okay. So for example, if I have like something to do off the cuff real quick, let's say r is equal to 2 now, a positive number. So the graph of this thing is going to be a circle of radius 2, right? And call that a circle of radius 2. There. That is 2. See how quickly we can graph them? Simply because we recognize the equation there. All right, let's take a look at another example here. In this next example, we're going to take a look at, let's look at the graph of a line this time. So I'm going to go this time theta equal, let's say pi over 4 or pi over 6. Doesn't matter. Some number. Now, to do this one, I can actually rewrite this as 0r now, because r is missing. 0r plus theta equals pi over 6. And this time, if I want to plot a few points, call it theta r, I'm going to choose any number you want for r. So for example, I'm going to go 0, 1, 2, like that. Well, the measure of the angle isn't going to change, right? Because 0 times anything is 0, so I just get simply the value of the angle, theta. Now let's plot the points. 0 and pi over 6 would be a point that's at the pole, right? And r1, 1 and pi over 6. So pi over 6 is this line, and 1 is here. That's a point there. Next point is 2 and pi over 6. Notice the measure of angle doesn't change, but the radial distance is allowed to change. So you can kind of see how this thing is going to go. These are for negative r values there. And if I connect the dots together, if I connect them, then I get this line. And there you have it. So this is the equation, theta equals pi over 6. The graph of that is going to be a line. Therefore, theta equal to constant. Let's just generalize this one now. Theta equal to a constant, call it, k, is going to be a line, right? That's going to be just a straight line. All right. Now, let's say I can, suppose I want to now, let's say I want to rewrite this in Cartesian form. Let's do our theta equal pi over 6. Okay. Now, pi over 6 here, if I pick a point here, for example, okay, any point, doesn't matter. One point on the graph of this is going to be 2 and pi over 6, right? I'm looking at that point. Okay. So I'm looking at this point. The coordinates of the points are 2 and pi over 6. So I can actually find the xy coordinates of the points, right? And I can say that tangent of theta, which is the ratio of y to x, is equal to tangent of pi over 4. And tangent of, pi over 6 is what I'm going with, right? Tangent of pi over 6. Now, what is tangent of 30 degrees? I can bring my special triangle, 30, 60, 90 triangle. There you go. This is 2, 1, 2, 3 labeled like that. So tangent of 30 degrees is going to be opposite over adjacent. It's going to be 1/3, right? 1/3. Well, the ratio of opposite to adjacent. So it's going to be, there you go. And I'm looking at, okay, it's going to be this right in here. There. This is going to be y, that's going to be x in this triangle. All right, so notice that's the slope of a line, by the way, correct? The slope of the line is, that's what y over x is. In Cartesian, that is the slope. All right, so I can write this equation as y is equal to mx plus b. And because the line goes through the origin, so b is 0, and the slope is 1/3, so y is equal 1/3 x. And that will be the equation of this green line drawn at pi over 6. Okay, and there you have this one. Now, let's take a look at another example here. In this next example, let's say I have r sine theta is equal to -1. And I want to graph this one. Well, I can quickly graph this one, and I'm not gonna use my grid because this is so simple. Remember, r sine theta, that's simply y, right? So I can graph this in Cartesian coordinate system, which is superimposed on top of a polar coordinate system. So here's my xy coordinate system, and let's say this is my polar axis right there, overlaid on top of the x-axis. And y equal -1, that's going to be a horizontal line at -1. And there it is. There's y equals -1. All right, and if I was going to do this on my grid here, I'm saving my grid for another example, but if I was going to do it there, so I go to -1 would be here below the x-axis, and that's going to be the graph. You see that? That's graph of y equals -1. All right. Now let's take a look at, how about another example? This next example, suppose I want to look at, I'm going to make it r cosine theta equals to 3. Now r cosine theta, remember, in Cartesian, that's just the x component of the point. And I get x equals 3. And once more, we recognize the equation in Cartesian, xy, 1, 2, 3, and that's going to be a vertical line, correct? A vertical line at 3. Now I can throw in my polar axis. There you go. And that will be the graph of x equal 3, or cosine theta 3. So if I want to do it on my grid, here is 1, 2, 3. You have a vertical line at 3. There we go. That'll be the graph on my polar grid. Okay. Therefore, r cosine theta is going to be a vertical line. R sine theta, that's going to be a horizontal line. Now, here is a gallery of the ones we've done and other polar equations that we can recognize and graph them. So the ones that we just did, the horizontal line, there you go. R sine theta, vertical line, r cosine theta. Those are the ones we've already done example of that one. And we've also done example of this one, right? Y equal to theta. Well, theta equal to a constant. And that one, if you convert it, by the way, it turns into y equal tan alpha x. And if theta is equal to alpha, remember, tangent of theta is y over x, right? And because theta is equal to alpha, so I can say tangent of alpha is equal to y over x. And if you cross multiply this, you get y is equal to x tan alpha, which is exactly what this is. All right, so there you have it. The fact that theta is equal to a constant, I'll look at this form. That would be the equation of a line that goes through the origin and has slope. Slope is theta, actually, right? For this one. Okay. Well, sorry, slope isn't theta. The slope would be y over x, which you get from tangent from right here. You know what I mean. All right, we did an example just a moment ago. Now, the circles, we've done one circle. The one I did was this one, remember? R is equal to A. And by the way, here, notice in this representation, A is taken to be positive, but even if A is negative, I did an example when it was negative. When A negative, either way you get a circle. It's just the radius is going to be absolute value of A if A is negative. Okay, so R equals A is going to be a circle center at 0, 0. And these are other parameterizations of circles also. Okay, the one that I did, this one, is the one that has radius, again, absolute value of A if you allow A to be negative, but the center is at the pole, 0, 0. These circles, these other two circles, are allowed to be off center. Okay, so the equation is R equal to plus or minus 2A cosine theta. With 2A parameterization, the radius will be A. Some books actually don't have 2, they just go A cosine theta. With A cosine theta, then the radius is 1/2 A. Then you go to A sine theta, so you're going to get a circle that's either up there or down here. With cosine theta parameterization, your circle could be on the right side or on the left side. Okay, just depending on whether you have a plus or minus. That's what the plus minus does. Okay, so the ones you're seeing, both of these, this is with the plus. With the minus, the circle looks like this. This is with a plus sine theta. This would be with minus. All right. Those are the circles. And again, going forward, I'm just going to cite what these are and use them directly. Now, let's take a look at more of these. And some of these, some of you may know this. Those of you who've never had trigonometry, you're going to find this interesting. For those who had it, there's a reminder. So we have these, these three. These are all Limousines. The general category, French. Limousin means snail. So that's what that is. It's French for snail. Okay. So you're looking at the graph of Limousins here. The Limousin could have either an inner loop or not have a loop. Whether it has a loop or not depends on the relationship between A and B. Okay. If A, notice in here, if A is less than B, that means the ratio of A to B, absolute value of A to B is less than 1, then there will be an inner loop. Okay, for the Limousin. If the ratio of absolute value of A to B is greater than 1, if it's greater than 1, then there is no loop. And if the ratio is 1, if the ratio of two things is 1, that means they're equal, right? A is equal to B. Well, if A is equal to B, then you get a cardioid. Isn't that cool? So cardioids, all cardioids are Limousins, but not every Limousin is a cardioid. Like here, this is not a cardioid, but it's a Limousin. So all cardioids are Limousines where A and B are equal. The ratio A to B is 1. Now, if the ratio of A to B, by the way, gets larger and larger, then the Limousin becomes more circular, and at some point it actually looks almost like this. It looks almost like a circle. Okay, except it has some kind of convexity. For instance, there you go, it may look like this. So right in here, it kind of bends a little bit. This is a Limousin where the ratio of A to B is greater than 2, actually. But you don't have to memorize that one. We'll just graph them. All right. So very important, folks, that we recognize these equations, okay, before we graph them. And in a few minutes, we'll see several graphs. Then we come to lemnis gates. These look like a propeller on an airplane, right? The propeller form of an equation. R squared is equal to A squared cosine 2 theta or A squared sine 2 theta. Now, these are the general graphs, by the way. So, for example, R squared A squared cosine 2 theta. The propeller may look like this. It may look like this. It may look like this. May look like this. It just really depends on theta here. So it could be rotated, in other words. But it will have, again, the propeller shape is going to have 2 parts to it that are symmetrical. All right. And let's see. Then we come to roses in both form, sine 3 theta and sine 2 theta, or cosine 3 theta, cosine 2 theta. In general, any equation that is in the form R equal to a sine n theta is going to be a rose. Okay. Now, if n is odd, the number of petals is going to have n petals of a rose. And remember, a rose petal is just a single part right in here. That's a petal. Okay. So if n is odd, then it will have as many petals. If n is even, the number of petals is going to be actually twice. It's going to have 2n petals. So for example, sine 4 theta is going to have 8 petals. Cosine 6 theta is going to have 12 petals. Those are more complicated to graph even. It just takes longer. With odds, that's good. You only get a single petal here. Now remember, here, that's going to be an odd number greater than 1. If you just go sine theta, right? And that graph, I don't know if we did it here, R equals sine theta, cosine theta. Oh, I didn't do one. Maybe we'll do one later. That's not going to give me a rose, okay, or sine theta. Maybe I'll graph that one next. Okay, so having done the gallery of these polar equations, let's take a look at some examples now. And again, I just want to remind for roses, if you just have R sine theta or just R cosine theta, not the multiple angles. Those are going to be circles. You see that right in here. Cosine theta, sine theta. So the only time you get a rose is when you have double angle and higher, when n is 2 or more. Okay, now let's take a look at some examples. All right, let's start with our first example here of these kinds of graphs. So in this example, let's say we want to graph a circle. So let's do R equals, say, 2 cosine theta. Let's see how we're going to do this. Now, a lot of people actually plot points. By plotting points means this. They say, well, theta is 0, 30 degrees, 45 degrees, 60 degrees, blah, blah, blah. And then they find the R and plot points and they connect the dots and they get the graph. Now, when we graph these polar equations, by the way, knowing is half the battle. Okay, so for example, R2 cosine theta, if I go back here, I can identify 2 cosine theta as this one. So I kind of know beforehand what it is that we're looking for, right? It's going to be a circle. And because it's positive 2 cosine theta, it's going to be a circle that's to the right of the pole. But knowing that, let's actually do this. So I'm going to start with, actually, instead of plotting points, I'm going to give it a range of values for theta. And then look at the range of R. Okay, so for example, I'm going to say as theta goes from 0 to pi over 2. Well, R, when theta is 0, cosine of 0 is 1, right? 1 times 2 is 2. So R starts, that's the starting point of the circle. The starting point is at R theta, 2, 0. So it's right in here, that's when it starts. Now at pi over 2, cosine of 90 degrees is 0. 0 times 2 is 0, so R is 0. So from 2 to 0, the point moves to 0 and pi over 2. 0 pi over 2 is going to be a point at the pole, right? And remember, we know we're looking for a circle, correct? So that's what that part of the graph is going to look like. You can see that. And of course, the radius of this circle is going to be 1, correct? The radius is 1, which is half of the number in front of cosine. Now, to complete this graph, my next range, I'm going to go from pi over 2 to pi. So that means the range is going to pick up from 0 to. Cosine of pi is negative 1. Negative 1 times 2 is negative 2. Therefore, the circle is going to come out of point 0 pi over 2, and it's going to go to point negative 2 and pi. Let's plot this point, negative 2 and pi. Well, to plot polar points with negative r, we start with a positive radius. 2 pi is going to be a point right here, right? This is 2 pi. 2 and pi. The negative 2 will reflect it 180 degrees across, right? So it ends up here. And remember, we're coming out of the pole. So this portion of the graph is going to look like so. There. And that completes the circle. So be careful with circle. You don't need to go from 0 to 2 pi to create a circle. All you have to go is from 0. Theta goes from 0, just like you saw, from 0 to pi. And that completes a circle. But there it is. Now we can actually get the Cartesian, the algebraic form of this if you like. And here's how you would do this. If you multiply both sides by r, okay, of the equation, so you get 2r cosine theta. All right, and then r squared is x squared plus y squared, and r cosine theta is x, correct? All right, now if I bring 2x to the left, I get x squared negative 2x plus y squared is equal to 0. And then I can complete the square on the left. Remember, to complete the square, I'm going to group the x's together, and then half of the coefficient on x, you square it. So that's going to be negative 1 squared is 1. I'm going to add 1 here, plus y squared is equal to 1. Because I added 1, I need to add 1 on the other side to maintain the balance of the equation. And within parentheses, we have a perfect square trinomial, right? And I can write this as x minus 1 squared, the square root of a binomial, plus y squared is equal to 1. And we recognize this as an equation of a circle whose center is at 1, 0, and the radius is 1. Those are the parameters of the circle. All right, and that's exactly what this is right there. The center of the circle is at 1, 0. Now, if you kind of think of this as your XY coordinate system, there you go. There's your XY axis. Now you have a circle that has radius 1 and is centered at 1, 0. Okay, and there you have that one. Good. Let's take a look at another circle here. Okay, so let me bring my polar grid first. All right, and this next example, we're going to look at, let's say, r equals -4 sine theta now. -4 sine theta. Again, if I want to know what the equation of the circle in Cartesian is, this is not a requirement, but it's good to get into a habit of doing, because in the future we will be expected to do this kind of stuff. Now I multiply both sides by r, and then r squared is x squared plus y squared, and bring 4r sine theta to the left. It's going to be positive 4 r sine theta is y, set it equal to 0. And then complete the square in y, so you get y squared plus 4y plus half of 4 squared is 4, and add 4 on the other side. And we can recognize this as, again, the squared form of y plus 2 squared equal 4. This is the equation of a circle whose center is at x0, y -2, and the radius is 2 square root of 4. True? So without going to polar, I can actually graph this, right? Center as 0, -2. That's 0, -2 is here, right? That's the center. Radius is 2, so from here then you just do a circle of radius 2 there, so you get something like that. That's going to be the graph. Now let's do the same graph in polar. Okay, so here's my polar axis now. Okay, and I'm going to do just like I did the previous example. I'm going to go with a range of r. There it is. Let's go range of theta first and then range of r, not the other way around. And that's range of r. Okay, so for my theta again, I'm going to go from 0 to pi over 2, and then I'm going to go from pi over 2 to pi. All circles are completed in a 0 to pi measure, radian. Now, when theta is 0, remember the equation is -4 sine theta. So sine of 0 is 0. So this circle actually starts at 0, 0, r theta. And then at pi over 2, sine of pi over 2 is 1, goes to -4, right? Goes to -4, and theta is pi over 2. Remember r theta. And then it goes from -4 at pi. Sine of pi is 0, goes from -4 and pi over 2. It finds its way back to 0. That's r and theta pi. Okay, now on my graph here, 0, 0 is here. See, I'm up here actually. I'm here plotting in my polar grid. So it says 0, 0, and then it goes to -4 and pi over 2. Well, this point up here, this is 4 and pi over 2 right up here. -4 pi over 2 will reflect it down here. You see that? Okay, so the circle is going to go like so. And then it goes from -4 pi over 2 to 0 and pi. Well, 0 and pi is going to be at the pole. And there you have the graph. So you see, you get the exact same thing. Again, knowing the graph, knowing what we're looking for definitely help doing this. Okay, now let's do something that ends up not being sine or cosine. So for example, what if I have something like r cosecant theta is equal to 8, something like that, and I want to graph this one? Well, cosecant, remember the reciprocal identity for cosecant is 1 over sine theta. So I'm going to go r over sine theta is equal to 8, and then I'm going to multiply both sides by sine theta. I get 8 sine theta. And this is the form of a circle, isn't it? You recognize that as the form of a circle. If you want the Cartesian form, it's easy. Multiply both sides by r, 8r sine theta, and that's x squared plus y squared, negative 8y. R sine theta is y. Add it to bring it to the left, and then you can complete the square on this one. You can do that step yourself. That's going to be y minus 4 squared is equal to 16. Reason for 16, because next step you're going to add 16 to both sides to complete the square in y. Okay, this is a circle centered at 0, 4, and the radius of 4. Okay, and I can graph this one. Let me... There you go. There's my polar grid. It's going to be a circle of radius 4. 1, 2, 3, 4. And oh, if I do my, like, how is it going to, where is it going to start? Oh, one thing here, by the way, sorry. The Cartesian form, nothing wrong with it, but with this, it doesn't, because I haven't plotted points, so I don't have a starting, ending, and I don't know how the circle is being created unless I plot points. So if I go to polar form, I look at the range of theta, and then I look at the range of r, I can actually see how the circle is being created, right? So for this one, what am I going to do for the the range of theta? Let's go from 0 to pi over 2, and then pi over 2 to pi. Okay, that means the equation is this one, 8 sine theta. So when theta is 0, sine is 0 is 0, r is 0. At pi over 2, sine is 1, so it goes from 0 to 8, right? 0 to 8, and then it goes from 8 back to 0. Now, because my grid here, again, the grid that you're looking at right in here goes to 4. I'm going to change these. So suppose this is now 2, 4, 6, 8. There you go. So I'm going from 0, 0 to at pi over 2, 0 to 8. So this is how it's going to go. It's going to go 0 to 8 like that. Okay. Of course, it's going to be a circle, correct? There. And then from 8 goes back to 0. Right there. So that's how your circle is generated, and the radius, of course, the center is there. 0, 4. And there you have the graph of this one. Okay. Now, enough of circles. Let's do something different. Let's try cardioid. How's that? The heart shape. And this is 2 plus 2 cosine theta. And we know the graph is going to be cardioid. Okay. Now, by the way, the letters oid. Okay. Oid means similar to, very similar to. And we know that cardioid means heart shape, right? Cardi, heart. Oid means similar to heart or heart shape. Well, let's do this one. Now we know we're looking for a cardioid, correct? And because these two numbers are the same, A and B are the same, so this is a Limousine, which is really a cardioid now. It's a subset of a Limousine. Now, to graph this one, this is how I do this. I'm going to look at the pole values. Okay, now what are pole values? Pole values are values where the graph crosses or reaches and touches the pole. We're talking about, remember, polar axis, this is where the pole is. So in other words, what I want to do, I want to know for what values of theta the graph's going to be at the pole. That's going to help me when I try to find my way to the pole. So I'm finding pole values. And remember, at pole values, r is 0, correct? So I'm going to set the equation 2 plus 2 cosine theta equal to 0. Then you can divide everything by 2 and isolate cosine. I get cosine theta equals -1. And between 0 and 2 pi, theta equal pi is a solution to that trig equation, right? Cosine of pi is -1. So when theta is pi, the graph reaches the pole. All right, and now let me erase this one, and I'm just gonna throw in again my polar graph here that I have. There you go. So I'm going to go again with my usual. I'm going to go range of theta and range of r and see how this turns out. Let's see. I'm going to go range of theta and range of r. Now for range of theta, I'm going to go from 0 to pi over 2. For the cardioids, pretty much you go every 90 degrees. And then I'm going to go from pi over 2 to pi, and then from pi to 3 pi over 2, and then 3 pi over 2 to 2 pi. Okay, so this is like my first range, second, third, and fourth range. Now these ranges, I'll be able to show you these on my graph in a few minutes. Now let's look at the range of r. That's when you plug in for theta into this equation. When theta is 0, cosine of 0 is 1. 1 by 2 is 2. 2 and 2 makes 4. That's the starting point of the cardioid. It's going to start at 0. Theta 0, R4. R4, theta 0 is actually this point right in here. That's 4 comma 0. That's the start of the graph. At pi over 2, cosine is 0, so r reaches 2. Okay, at pi over 2, r is 2. So this is going to be right in here. At 90 degrees, it reaches the radius of 2. So that's 2 and pi over 2. And then it's going to go, where is it going to go? From 2 to pole value pi goes from 2 to 0. Okay, so it's going to end up right in here. That's 2, 0. And then from 0 to, at 3 pi over 2, cosine of 3 pi over 2 is 0. So r is equal to 2. So at 3 pi over 2, it reaches 2 right in here. Again, this is 2 and 3 pi over 2. And finally, it works its way from 2 to, at 2 pi, cosine 2 pi is 1. 1 by 2, 2 plus 2 is 4. It finds its way back to 4 right in here on the way back. So on the return, that's 4 comma 2 pi. All right, and we should be able to graph this, what you call it, this cardioid now. So remember the first part of it was like this, second part, and then third part, and then it goes back to, let's probably come out more and go. There you go, that's just the general shape. As long as I don't draw a rose or let's say a circle, you know that this is a cardioid. And there you have it. That will be the graph of that polar equation, a cardioid. Now, these ranges that I selected, I can actually show you now these on the graph. So this was part 1, part 2, part 3, and this was part 4 of the graph. From here to here, part 1, there are 2, this is 3, and that's 4. And because we actually move in a counterclockwise direction for theta, the graph also moves in the same direction. We can actually attach something cool, put arrows on it if you like, and that shows you what we call the orientation of that curve of that cardioid. Okay, and there you have this one. Let's take a look at another one. For this next one, suppose now I want to do a Limousine. Okay, I'm trying to do one of each of these so you have a reference for one of each of them. This one we know is a Limousine. Okay, because it looks like r equals a minus b cosine theta in our gallery of functions. Now, this is a Limousine, and this is going to be a Limousine without a loop. It doesn't have a loop because the ratio of a to b, if you look at absolute value of a to b, that's going to be 4 to negative 2, and that's 2 is greater than 1. So it's actually going to be what we call a convex. This is a convex Limousine. That means it's nearly circular. Nearly circular. Okay, so let me see whether the graph is going to reach the pole or cross the pole. So I'm going to go pole values, if they exist. For that, we set the equation equal to 0. So this means negative 2 cosine theta equals negative 4, or cosine theta divided by negative 2 on both sides. Cosine theta equals 2, and of course we know that the range of cosine is negative 1 to 1. It can never equal to 2, so there are no pole values. In other words, this graph will never reach the pole. It will probably go around it, but never actually touch nor cross the pole. So I'm going to go with my ranges here. I'm going to go range of theta, and then I'm going to go range of r. And for range of theta, I go 0 to pi over 2. And again, for your Limousines, pretty much you go, unless there's a loop. I'll do one with a loop. But if it doesn't have a loop, your Limousine doesn't have a loop, you go every 90 degrees, the way I'm doing it. I'm going to go pi to 3 pi over 2, and then I'm going to go 3 pi over 2 to 2 pi. Cardio is the same thing, because cardios are Limousines. Okay, now you plug in for theta into this equation. And when theta is 0, again, cosine 0 is 1, 4 minus 2 is 2. At pi over 2, cosine is 0, so r is 4. And then it goes from 4 to, at pi, cosine is negative 1, times negative 2 is 2, and 4 makes 6. And then coming out of 6, at 3 pi over 2, cosine is 0, so it goes to 4. And then at 4 at 2 pi, cosine 2 pi 1 by 2, 4 minus 2 is 2. There you have it. Those are the ranges. Now let me again throw in my polar grid, and this time again I'm gonna go 2, 4, 6, 8 on the scales here, okay, because I need to go all the way to 6. At 0, when theta is 0, r is 2, so you're over here. Okay, at pi over 2, it reaches 4. And then it goes from 4, at pi, it goes to 6, and this is 6. So it goes from 2 to 4 to 6. At 3 pi over 2 is back to 4. And then at 2 pi, it goes back to 2 here. And so there you go. And that's what this thing will look like. And that is the graph. Again, you can do much better graphs, of course, with the software, right? But the idea here is how I do it without the software. And there you have it. Guess if I bold it and go over it enough times, it's going to look like a circle almost. It's not a perfect circle, by the way, so I don't want to make it like a circle. And here's the, right here, the pole, not near the, sorry, this is the pole. I'll never touch the pole. This is the convex point. Okay, right there. All right, at 2, 0. And that's the graph of that Limousine without a loop. Now, what if it has a loop? Let's actually take a look at one. I'm going to make one that has a loop. So let's say the ratio has to be less than 1. I'm going to go 1 minus 2 sine theta. Okay, again, the absolute value of 1 to negative 2 is 1/2 less than 1. So this one is going to be a Limousine with an inner loop. Now, here's where the pole values are going to really help me. So let's start again with our pole values. For what value or values will the graph be at the pole? It will reach the pole. Either go through it or touch it. So I'm going to set the equation equals 0 because r is 0. At pole, r is 0, right? Theta could be anything, by the way. Now, if I solve this, to solve, you subtract 1 divided by 2. So sine theta is 1/2. And we solve that equation, which is a simple trig equation. Sine of what angle is 1/2? That's actually special angle. Sine of 30 degrees and sine of 150 degrees, right? 5 pi over 6, if you recall, right in here at pi over 6, and over here 5 pi over 6. Both of these have sine that is 1/2. Okay, we're good to go. So let me start by range of theta, and then I'm going to have my range of r. Good. Now, so here's how my ranges go. I'm not going to go 0 to pi over 2. Remember, for Limousine you do, but not for, for Limousines without a loop you do, or cardioids, but not for Limousines with an inner loop. So I'm going to go from 0, and it looks like on my way to pi over 2, 90 degrees, I have to pick up 30 degrees, pi over 6 here. So I'm going to go from 0 to pi over 6. And then it's not going to reach the pole any longer until 5 pi over 6, right? Which is, what, 150 degrees? So I'm just going to go to 90 degrees, and then from 90 degrees, I'm going to pick up 5 pi over 6 on my way to 180 degrees. You see how that works? There. Now, because I know it's not going to be at pole beyond that any longer, I already picked up my pole values, right? Pi over 6, 5 pi over 6. So from here until I reach 2 pi, I'm going to go every 90 degrees. So I'm going to go from pi to 3 pi over 2, because I know it's not going to go through the pole, and 3 pi over 2 to 2 pi. See how those ranges work? Okay. Now plug it into range of r. Let me put r here so we know what it is. 1 minus 2 sine theta. This is what I'm plugging my theta into. So theta is 0, sine of 0 is 0, so that's 1. That's the start of the graph. The graph starts at 1, 0. Okay. At pi over 6. And then it goes from 1 at pi over 6, that's 0 because That's what we found here. Those are my pole values. Pi over 6, 0, 5 pi over 6, 0. So I went in and put those zeros there. Okay. Now it goes at pi over 2. Sine of 90 degrees is 1. Times 2 is 2. 1 minus 2 is negative 1. Negative 1 to 0. At pi, sine of pi is 0. So we get 1 minus 0. And then from 1 goes sine of 3 pi over 2. That's negative 1 times negative 2 is 2, and 1 is 3. Goes from 1 to 3. And it goes from 3 to at 2 pi. Sine of 2 pi is 0. So it ends up with 1. There you go. Now let's actually plot these points. Let's see here. I'm gonna save it with this grid that I downloaded because it has pi over 6. My earlier ones had pi over 4. Okay, well, let's do this. Enlarge it a little bit. Now here's how it goes. Remember, the start of the graph is at r theta. That's 1, 0. Now for this one, I'm going to stay with this one. Okay, 1, 0. So that's the start of the graph. And then at pi over 6, it reaches the pole right here. That's that part of it. The next part goes from 0. At pi over 2, it goes to negative 1. Well, pi over 2 and 1 is this point. Pi over 2 negative 1 will be this point. True. So it's going to go like that. That's the second segment. Okay. And then from negative 1 at 5 pi over 6, this is 5 pi over 6, goes to 0. So it's going to go to 0. So you get this loop right in here. Indeed, that's the inner loop. Okay, and then what happens? From 5 pi over 6 to pi, it goes to 1. So my point is r, 1, and theta is pi. 1 and pi is this point right here. And that's the next part. And then it goes from 1 pi at 3 pi over 2, which is here. 3 pi over 2, it reaches 3. Reaches right down here, 3, a radius of 3. There. And then from 3, it works its way back to 1. So that's going to be r theta. 1 and 2 pi on the return, that's 2 pi. And 1 is going to be exactly this point. There. And that's going to be the graph of this Limousin. Isn't that cool? So using the range of theta really makes sense to me, and I like doing it this way. So you can plot points again and look how this thing's going to go. Now my ranges. This was my first range. This is my second range. Then I came here third. Then I went here fourth. This was my fifth. This was my sixth range. If I number these 1, 2, 3, 4, 5, 6. So I know exactly how this, if this is a moving particle, a moving object, I know the starting point of the motion. I know exactly, I can trace the motion of this item, this particle again, or this subject. And from start to finish. And there we have that one. Okay. Now, let's take a look at a rose. I like to do a rose and maybe a lemniscate. And that way I've done one of every example for you. Okay, let's start with a rose. Okay, I'm going to go 3 cosine 2 theta. This is going to be a 4-petal rose, right? It's going to be a full 4-petal rose. And like before, I'm going to look at my pole values. So I'm going to set cosine 2 theta equal to 0. So from this 2 theta, the zeros of cosine are at pi over 2 plus k pi, where k is an integer, right? And divide both sides by 2, I get pi over 4 plus k pi over 2. So that's pi over 2k. That means it starts at pi over 4, then every 90 degrees. That's where the pole values are. So to write a few pole values between 0 and 2 pi, when k is 0, pi over 4. When k is 1, you have pi over 4 plus pi over 2, that's 3 pi over 4. That's like 45 plus 90. Correct? 3 pi over 4. The next one is going to be 5 pi over 4 and ultimately 7 pi over 4. So these are again the points where that rose will reach the pole, okay, at 4 different times. Okay, now I could, let me also do this. I like to also kind of bring in the regular graph of cosine into this. Okay, so what do I mean by that? Well, think about the graph of separately in like earlier chapters. 3 cosine 2 theta. This is now Cartesian. Okay, I'm not in polar. So sidetrack. Okay, or sidebar. We're going to another part. 3 cosine 2 theta. Well, the period of this cosine function is 2 pi over 2, which is pi. It's 2 pi over this number. Okay, and remember the way I graph these? You set 2 theta between 0 and 2 pi to get one cycle. And the cycle here shows the start ending point of the wave, and it gives you the period. The period is also pi. I can get that from my interval. Now if I graph this one, this I can graph easily, right? Here's one cosine wave. Here's a second cosine wave. The first one completes from 0 to pi. The second wave completes from 0 to 2 pi. True? Okay, halfway. This is going to be pi over 2. So the tick mark so far is pi over 2 pi. This would be 3 pi over 2, and then 2 pi here. Now if I go halfway between 0 and pi over 2, that's where I get the intercept. That's pi over 4. This one would be 3 pi over 4. This one 5 pi over 4. This one 7 pi over 4. Now check these out and check these out. Isn't that cool? Those are the pole values. The pole values are the zeros of the regular cosine function too, of this cosine 2 theta. The amplitude, of course, is 3, so that's up 3, negative 3. And we are good with this one. Let's make that negative 3. Cool. And then I have this one. So why did I do this, right? Well, here's why. Because I'm about to do the ranges, and I can kind of marry the two together in order to graph this thing. So let me actually do my range of theta here, and a range of r. Maybe we'll just graph this quickly using the way I'm doing it the way I do. So I'm going to go always start at 0. So I'm going to go 0, not to pi over 2, but on the way, I like quadrantal angles, 90, 180, 270, 360, but on the way to these quadrantal angles, if there are pole values, I need to stop and pick them up. So the first pole value is at pi over 4. And then from pi over 4, I'm going to go to pi over 2. See that? I couldn't go directly from 0 to pi over 2 because I would miss that pole value. And then I go from pi over 2 until the next pole value is 3 pi over 4. And then you go 3 pi over 4. I'm sorry. Pi over 2, I go to, let's see, yeah, 3 pi, no, I'm not sorry. It is 3 pi over 4. And then I go from 3 pi over 4 to pi, okay, and so on. But so far, let's see what happens. And I try to kind of bring in this graph in with what I'm doing. Now the ranges, when theta is 0, cosine of 2 theta is going to be cosine of 0, which is 1. The start of the graph is at 3, 0. Pi over 2, I reach the pole, then I come out of the pole. Pi over 2 cosine of 2 times pi over 2, that's cosine of pi. Negative 1 times 3 is negative 3, right? Negative 3 goes to 0, and then from 0 to at pi, cosine 2 pi is 1. 1 times 3 is 3. So there you have it. Let's see what we got here so far. So starting, I'm doing just this part. As theta goes from 0 to pi over 2. So on my graph now, I'm going like this. From 0 to pi over 4. So the rows is going from, the pedal is going from 3 to 0, right? So this gives me half a pedal, right? And then from 0 to negative 3, I pick up another half a pedal right here. And then each time, notice, every 45 degrees, I pick up half a pedal there. You see that on this graph? Now, I know that I need to have a 4 pedal rows, right? So from here to here, I need to go 1, 2, 3, and actually, yeah, I gotta go all the way to 2 pi and possibly beyond to do this. Okay, let me bring the graph, my grid, and let's graph this thing now. We're going to graph the rows right next to this. Okay, ready? Let's do this. The starting point is R3, right? R is 3, theta 0. That's the starting point. At pi over 4, this is pi over 4, we reach 0 right in here. So that's that part of pedal of a rose. And then at pi over 2, it goes to negative 3. Well, 3 and pi over 2 is this point. Negative 3 would be this point. And check this out. You see how that works? So it goes like this, and then it actually works like so. So it doesn't loop like this, right? It actually moves below the pole. And then where is it going to go? Well, when it works to 3 pi over 4, it reaches 0. That's this point right here. So it goes 3 to 0, 0 to negative 3. Oh, 3 pi over 4 and 0. The 3 pi over 4 is this one, and 0. So it's going to come back and touch the pole. It's going to be at the pole there. And then it goes to 0.3 pi. Well, 3 pi is this point. It's going to go here. And that way I have, I don't have full 3 pedal rows, right? I only have half the graph done. Okay. So you can see how this works now, hopefully. So by the time I reach pi, this is where I am on the graph here, right? Remember, it went from 3 to 0, that's this part. And then from 0 to negative 3, that's this part, 1, 2. And then from negative 3 back to 0, that's this part. And then from 0 back to 3 at pi, right here. See? This one gives you half of the rows. The other half is when you go from pi to 2 pi, that will complete it. Okay, so I got my 1, 2, 3, this is 4. The next part, you can verify this. This will be fifth segment, and the sixth segment will actually go up here, and the seventh one goes this way, and the eighth will wrap it up, will close it up. Okay, and this would be your rows. Now my rows is in there. Just that looks a little better. All right, and there you have that one. Again, 1, 2, 3, 4, 5, 6. This is 7, and this was 8. And you have a complete rows there. Imagine if this was like 6 petal rows or 8 petal rows, it would take longer, but again, you can do it. It can be done. Okay, let's finish this one. Let's finish it with a lemniscate. This time I have r squared sine 2 theta. This is going to be a lemniscate. The propeller ones, right? So let's start like before. My pole values. I'm going to let sine 2 theta equal 0. That's r0. And from this, the zeros of sine are at k pi. Therefore, divide by 2 at k pi 2. So that means that's 0 and then every 90 degrees. Correct? And good. So some zeros are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. Now, for example, let's say when the theta is, well, if theta is 0, if r squared is, because sine of 0 is 0, then you get r is 0, right? So for any one of these, that's what's going to happen. R is 0. Let's see. So I'm going to choose the range of theta and range of r again this way. For theta, I'm going to go from 0 to pi over 4. Okay, and let's see what happens to the range of r. So I'm going pi over 4. Therefore, r squared is sine 2 times pi over 4, which is sine of pi over 2. And that's 1. From this, if you take the square root, I'm going to get, what, plus or minus. Don't forget, when you take the square root, you have plus or minus 1. So we actually, there are 2 points corresponding to that. One of them is 1 and pi over 4. The other one is negative 1 and pi over 4. So we actually have 2 points. Okay, and then I'm going to go from pi over 4 to pi over 2, my pole value. Pi over 2, I'm going to go from plus minus 1 to 0. And then let's say I'm going to go from pi over 2 to 3 pi over 4. Okay. And from 3 pi over 4 to pi. Now, let's try, sorry, this plus minus 1. Here I dropped the 1. Now, let's try at 3 pi over 4, right? Because here we are at 0. I want to know where it's going to go to. R squared is equal to sine 2 times 3 pi over 4. That's going to be 3 pi over 2. Sine of that is negative 1. R squared negative 1. So R is going to plus minus square root of negative 1 plus minus I, which is not real. Therefore, the graph doesn't exist there, right? At this point, we're going to get not real, which tells me from pi over 2 to 3 pi over 4, right? And subsequently from 3 pi over 4 to pi. And here, the graph does not exist. So there's no graph. There is no graph here between pi over 2 and pi. All right, let's see if we know enough to graph this. And then knowing it's a lemniscate and using the symmetry, let's see if I know enough to graph this one. All right, the points. Start of a point is R00. So this thing actually starts at the pole right in here. And then, let's see, at pi over 4, it reaches 1 minus 1. So I'm actually plotting these 2 points. 1 pi over 4 and negative 1 pi over 4. Well, and let me make this 1 now, because I want this to be meaningful. So this would be like 1/2, 3/2, 4/2. I just want my graph to be magnified somewhat. Okay. Pi over 4 and 1. Pi over 4, 1 is this point. And then pi over 4, negative 1 will be this point, right? You reflect it. So you get negative 1 and pi over 4 there. Okay. This one, 1 and pi over 4. Reflect it, you get negative 1 and pi over 4. Remember, between pi over 2 and pi, there is no graph. So here, there's nothing here. And then from pi over 4 to pi over 2, it goes from negative 1 or plus 1 to 0. By the time we get pi over 2, we are at 0. There. And this one goes to 0 like that. Okay. Now, because we know we're looking for a propeller graph, and how do we know that? Because we have our gallery of functions here. Remember, we know that the lemniscate is going to look like that. Therefore, we can complete the graph without plotting future points. This is taking advantage of the symmetry that we see. Can complete that portion, and then this portion of the graph, and the graph is complete. Okay, so this is how you would graph a lemniscate. Now, there are again variations on how you do it. A lot of people just plot points. I like choosing a range of an angle and then finding the range of theta. The pole values are absolute must. If they exist, they definitely help you. And there you have it. So with this, we are done with this lecture. Sorry, it went a little long, but then really, it's because the subject required it. And we did many examples, almost a dozen examples from each of these polar equations. So hopefully you find it useful. And with that, we are finished with this lecture. Thank you for watching, everyone, and hope to see you in the next one.